So now that we've finished talking about properties 8, 9, and 10, which were our comparison properties, let's see how we can use these to go ahead and answer a question like example number 4. Here I'm going to be asked to use the properties of integrals to estimate the value of this specific integral. Now actually, this is a question that was discussed in our very first section in this class. We were interested in how we might be able to determine the area under this curve from -1 to 1. Now, again, this is going to be extremely difficult to do if I wanted to try to start setting this up, again, as a limit as n approaches infinity of a gigantic sum. Like, this is going to be really, really terrible to do with this particular approach. And if you don't believe me, you could try to go ahead and start setting it up and just see how terrible it becomes. So this is why, again, it might be helpful to be able to use these comparison properties to figure out roughly what this value is. Okay, so here's what I'm going to go ahead and actually do to start. First off, if I wanted to, I could go and sketch a quick picture of what this function actually looks like. Now, again, a picture of this was kind of shown on the first day of class, but I'm going to have a picture that looks something kind of like this. And so on the interval, say from -1 to the value of 1, I'm going to get some area that maybe resembles something loosely like the following. So this is the area that I'm attempting to try to find. Now, what's kind of interesting about this is to note that if I want to use any of my comparison properties up above, I have to start by considering the interval that I'm working on. And if I want to try to estimate the value of this integral, property 10 seems particularly useful. So here's where I'm going to go ahead and actually start. I'll start by saying that we note that our value of x is actually going to be between -1 and 1. Those are the only values that I'm working with. And we are working obviously with the function of 1 over x squared plus 1. Now, if I want to use property 10, I need to create my f of x function being bounded by two different numbers. I need to create a number, a y value that's always bigger than my function, and a little m value that's always smaller than my function. Okay, so we're going to go ahead and try to do this here and think about this algebraically. So let's take a look. I'm going to start with the thing that I know, which is the interval of x's that I'm working on. And much like we did with our squeeze theorem, actually, way back in our first chapter, is we said maybe what I could do is I could take this and begin to manipulate it. So that way it would start to have this inside piece look like my function, f of x. So take a look. I'm going to start this here by saying if I took all the numbers from -1 to 1, if I took any number at all from -1 to 1, and I squared any value from -1 to 1, what would be the only types of values that I could have left? Well, the values that I should end up with would only be values from 0 to 1. Notice I didn't square all three things here. That's not what I was doing. I was thinking about if I took every number from -1 to 1 and I squared all of them, then where would the results actually fall? The results, if I took all these x's and I squared them, could only ever be 0 or positive, so they could only exist from 0 to 1. Well, if that's the case, notice that I've now introduced an x squared, which is something that's included in my function, which is good. Now I'm going to go ahead and note that if I wanted to figure out where x squared plus 1 would be, well, that's pretty easy, because if I took a number that was somewhere from 0 to 1, and I added 1 to it, it would now be a number somewhere from 1 to 2. That's just common sense. But now I could go ahead and make one final adjustment. I could state here that this implies that if I did 1 over x squared plus 1, notice that's my function f of x, I have to think carefully here about what's going to happen. Notice that if I just took every number and I put it on the bottom of a fraction, this would be a completely ridiculous statement, because there's no way that 1/2 is larger than 1. When I put this largest value into the denominator of a fraction, I actually generate a smallest value. And so I'm going to end up here with 1/2 and then the value 1. Okay, so now that I have this, I can see that I have found that my function is always going to be wedged between the values of 1 and 1/2. In the picture here, the value of 1/2 would look something, I don't know, say like the following. Maybe this is where 1/2 is in my picture. This is the height of 1/2, and maybe up here is where the height of 1 is. So I can see that my black curve is perfectly in between those on this interval. And so this is a perfect time then to make use of property 10. If my function is wedged between two values on my interval, then the area underneath the green is smallest, the area underneath the blue is largest, and the area underneath my function happens to be the middle value. So I can go ahead and state this. Oops, and I'll change my color here back. So I can say, by property 10, we have that the integral from -1 to 1 of 1 over x squared plus 1 has to be wedged between the integral from -1 to 1 of 1, that is the area underneath 1, and the area underneath 1/2. Of course, evaluating those outer areas is really, really easy, because I just noticed that these are going to be areas of little rectangles, and so I can quickly find their area. Let's see, the area of this green rectangle would be, let's see, my interval is 2 units wide and 1/2 tall. So my green area here would be 1/2 times 2, and this would be 1 times 2. And so I can arrive at the final conclusion that the area in red up above has to be, it must fall between the value of 1 and the value of 2. So again, this begins to answer that question that we actually posed in our very, very first section. I know this red area is somewhere from 1 to 2. I'm not precisely sure of its value, but I know it's somewhere between 1 and 2.